Good afternoon. It's a pleasure to be here with you this afternoon in this unique and very impressive facility. As your lead-off speaker this afternoon, what I'm going to talk to you about regarding C-grid reinforced technology to make carbon cast precast elements, as well as technology for infrastructure and other concrete construction products. It's been the labor of my love in life for the last 15 years. I was the Director of Commercial Development for Chomera North America for 12 of the 15 years, and for the last 3 years I've been the Executive Director for the Altus Group. So my presentation is going to be about the history and technology of C-grid technology. The title for my presentation today is C-grid Reinforcement, Innovative Composite Solution for Eliminating Corrosion in Concrete Construction and Repair. So I'm going to cover the waterfront and give you a very good primer on carbon fiber grid reinforcing technology, carbon fiber reinforcement, and how it's applied to today's commercial construction solutions in a variety of aspects, and corrosion is just but one aspect. So with that, here we go. Let's get started. A little bit about the history, how we manufacture the carbon fiber grid. We'll talk about the mechanical and the physical properties of the grid, which then our speakers later today will translate further into design and implementation discussion. I'm going to give you some precursor on how carbon fiber grid infrastructure and repair applications, successful projects that have been completed over the last 10 years since the development, and then wrap up with some commercial construction. So I have 45 minutes to do this, so hopefully I'll give you a very good primer. First, how was the technology developed and introduced? C-grid reinforcement was developed by Chomera. Chomera is a French company located in the Ardèche region. It's basically a family-owned fourth-generation company. They have 3 business units, which are textiles, composites, and fashion and industrial specialty elements. The business sector that where C-grid belongs is actually in the composites arena. And the C-grid technology was originally developed in France using a pilot facility that they had. Product was brought to the United States for initial commercial development, and then we built a brand new plant in Anderson, South Carolina. So I'll show you some of the aspects of that. So that's a little bit about Chomera, 1,700 employees, multi-million euro conglomerate corporation. The products that really helped spur the development were originally textile-based products using thermoplastic resins. However, we refer to the products as non-woven laid scrims, and Chomera developed what's known as a rotary trammer process, which allowed the products to be made in a very economical, low-cost fashion. The major markets for the textile-based products were underlayments for ceramic tiles. We refer to them as cement boards, roofing membrane products, sailcloth. I'm sure many of you have seen the America's Cup races, and many of those fabrics are used on high-speed racing boats because they want high-performance textile fabrics. And then the infrastructure products really comprise of products for paving, repair, and precast, which is the C-grid technology. So that's a little bit of the overview of Chomera. C-grid, what is it? It is a novel, patented product which was made using the Chomera's rotary forming technology, and specifically carbon fiber and epoxy resin, which allowed low-cost continuous CFRP reinforcement. So that's the technology you hear me talking about today, CFRP, carbon fiber reinforced polymer. And one of the aspects, obviously, is the corrosion resistance of the material, as shown by comparison to steel in its form. A little bit on the structure of product. It is not a woven textile as you would traditionally know it. It is a cross-laid scrim. The filaments are laid parallel to each other in a 0-90 fashion, and they are never in a curved position. They're always in a planar position. The formulation for the epoxy is proprietary. It's a high TG chemistry which resists fire and has a very high transition point. The epoxy is thermocatalytic. It cures upon contact with heat, so it moves from a liquid to a solid in the manufacturing process. And from start to finish, the process takes about 3 minutes to make a carbon fiber grid. It is not labor-intensive process. It is a highly capital-intensive investment, totaling some $5.5 million US, to make grid structures up to 2.6 meters in width. So just a little further elaboration on that. The products are primarily used as steel reinforcements to replace traditional steel reinforcements, welded wire mesh, for concrete or other masonry applications. They are not geotechnical fabrics, they're not membranes, and they're not graded products because they are made in an in situ process. The filaments used in the construction of the product are continuous and flexible, and the products are delivered on roll goods or in specific sizes and sheeted elements, as you'll see going forward. Now, this is a photomicrograph of the actual polymeric structure of the composite, and the picture on the bottom is actually the first roll of carbon fiber grid we ever produced, 1 meter wide. So all the initial development in the first 3 years were all based on 1 meter wide products. Since then, we've expanded to 2.6 meter wide products. It's high speed. The carbon fiber to epoxy ratio is approximately 55% carbon, 40 to 45% epoxy. This is one of the things that actually made the technology viable, which was the ability to produce a carbon fiber composite structure that could economically compete and replace steel when viewed in a systematic approach. This is on the left, you see a product in wide width roll formation coming off the back end of the machine, and that's about as close as you'll see the technology to the manufacturing, because it is considered art, manufacturing art by Chamorro. Every roll of product is tested for weight. It's also tested for tensile. And tensile is the predominant property that you're looking for in the using of a carbon fiber grid. So the products have guaranteed strength minimums with minimum average roll values. So strength is the property that we're selling, designing, and using. And why? Well, it's very simple. It's a very thin cross-sectional area, roughly between 1 to 3 millimeters in thickness. The grids are engineered to provide the right amount of strength in each direction that you need. The grids can be bidirectional or unidirectional. Here we're just showing the differences in apertures and structures that are made for the various products and applications. Because carbon is fairly expensive, you only want to use the amount of carbon fiber you need in a specific application. So there's a whole range of products in the portfolio to allow that to be cost effective. And again, the structures can be bidirectional or unidirectional. The picture on the bottom is actually a shear truss element. You'll hear our future speakers talk about that more as we get into wall panel and architectural discussions where the product is used as a shear connector. Here it's sold in discrete widths in 1.6 meter lengths to give you some comparison idea. This is the product portfolio as it exists today, and we identify it by nomenclature C50, C12, C25, C100. Those specifically refer to the amount of carbon fiber tows or filaments that are used in an individual strand of product, a single strand of carbon fiber tow. So in this case, there would be 50,000 individual filaments, finer than a human hair, comprising a carbon fiber tow. In this case, there would be 12,000. 25,000, or in some cases, if you need a very heavy carbon fiber grid, you'll use up to 100,000 filaments to deliver the strength required for a specific application. What is the competition to carbon fiber grid that exists in the world? And there are some other types of composite CFRP forms. In Asia, there is a product called NEFMAC. They use it for tunnel linings, but it is a grating product, and it is 10 times the thickness of the C grid and 10 times the price. There are other woven textile product meshes that you may read about from time to time. One is Sigrid-Tex, the other is alkali-resistant grid fabrics. Those are thermoplastic coated textile fabrics. They have curvature in the products. They are not planar in structure, and therefore they don't deliver the strength that you would get with a CFRP reinforcement. And more commonly, what we are competing against is welded wire mesh, other steel corrosive reinforcements, MMFX, rebar, or other forms of FRP composite materials. Products sold in various forms: master rolls, sheets, shear grid, kits, decor, and as you can see, it produces a lot of product on a roll. So each of the products are nested in styrofoam and packaged for shipment. Let's talk a little bit about the grid and material characteristics that are common with carbon fiber, but more specifically to the grid. This graph really shows the comparison of carbon versus other fiber materials, glass and aramid. They're commonly used in the construction markets and applications. The glass is most typically a E-glass product. AR glass is somewhat similar. Aramid, much higher strength. Most people refer to aramids as the Kevlar types of fibers used in ballistics. It's predominantly used in construction for confinement applications because it has poor chemical resistance of alkalinity, so it's not generally used in situ with concrete. And carbon, which the structures are all linear elastic, as you see, and that's typical of all high-performance fiber materials. Again, comparing it to steel structures, something that you may be familiar with, carbon fiber grid in terms of tensile strength, and comparing it to a post-tension steel strand, or comparing it to a light rebar structure. So the steel structures exhibit ductile behavior. They load and elongate or yield, whereas the carbon fiber materials are always linear elastic. They load to ultimate failure. Again, Barbie and Pat will talk more specifically about that. From an environmental standpoint, chemical resistance. Carbon fiber is essentially chemically inert. The epoxy is very resistant to most elements. And in North America, where most of the durability work has been done for transportation structures, it has been proven that carbon fiber structures, CFRPs, can retain about 90% of their tensile strength over the duration of exposure. Unlike glass structures, which see onset of alkali deterioration over time and loss of properties to the magnitude of somewhere in the neighborhood of 60%. So considerably different, and also the carbon fiber is much stronger. When you put a carbon fiber grid into a concrete section, like the one shown here, basically over 200 millimeters thick, and you subject it to 4-point loading, what you see is pseudo-ductile behavior. You see the concrete starting to load, concrete crack, to failure of the product. So that's a typical stress-strain curve for a concrete beam section reinforced with a carbon fiber grid element. Material, another property that is beneficial, and I'm sure you've all read about the aerospace industry or the automotive industry and its drive for lighter weight, for fuel efficiency. Well, the concrete construction industry uses it for the same reasons: lightweight, high-strength structures. But it also has one unique characteristic, and that is fatigue behavior. the performance of a repeated loading the structure is very, very good. You can actually load a section and cycle it thousands and millions of times without fatigue failure. So that's one of the reasons the automotive and aerospace structures like carbon fiber composites. It's a unique property to FRP materials, and also can be subjected to highly sustained loading. So the bottom graph shows the loading fatigue performance behavior. In your sheets on your chairs are typical properties of some of the various carbon fiber grids I detailed earlier, the different aperture spacings, which range from 45 by 40 up to 320 by 60. So again, we're trying to develop the right type of structure for the specific type of application. The tensile strength depends on the size and the spacing of the carbon fiber strand. And the good thing about carbon fiber composites is the modulus is very similar to steel, so it makes it easy to design and replace from an engineering standpoint. So how does it compare to, say, a welded wire mesh? Well, quite simply, grids do not corrode. They are not ductile. They do have a similar modulus to steel, but they are somewhat comparable to lighter bars and light welded wire fabrics. Where you use them predominantly is temperature and shrinkage reinforcement applications, light structural reinforcement, generally a secondary reinforcement, and in applications where you seek corrosion resistance or weight reduction. Where is the concrete CFRP used today? Well, precast concrete, and we'll talk about many of these applications as we go through the presentation today. Insulated sandwich wall panels, architectural cladding, double Ts, very, very significant major market for floor or roof elements, piling. We'll talk about some of the non-precast applications, which are cast in place, pervious. If you're going to reinforce a pervious concrete, the only solution is a non-corrosive reinforcement material. And then the repair applications, shotcrete, overlays, ferrous cement, timber repair, and others. And I'll give you some specific examples. In our case, the concrete, the C-grid reinforcement is generally always used inside a concrete structure, integral. However, it could be used externally if it's mechanically fastened. And you can externally bond the material with cementitious or polymeric materials, like polyurea or polymer modified concrete, some of the high technology materials that are on the market today. They resist tension forces, and they can be used in combination with traditional reinforcing materials to achieve desired products like steel reinforcement. So why use carbon fiber grids? Well, they provide a lot of advantages that outweigh higher material cost, i.e. durability, long-term performance, insulation value, and you have to view the systems in a systems approach as opposed to a one-to-one material substitution, because carbon fiber grids will always cost more than the materials they are going to try and replace. And the cost benefits are deeply rooted, and you must view them in a systems approach as opposed to a one-to-one substitution. Materials are supplied in rolls. They're easy to ship and handle versus steel. In actuality, you get more product on the truck than you would if you were using a steel reinforcement. They're easy to cut, position, and install. And one key thing that we have is that if you think out of the box, as our group has done, you can look at the possibility for automation and labor savings opportunities. Corrosion resistance and durability goes unspoken. The picture in the right basically shows several weeks of what happens to the steel in a aqueous environment. When you start thinking about non-corrosive reinforcement elements, then you can think about the system, which is panels can be lighter, lower handling, shipping costs. You can expand the reach of your precast plants. You can also reduce the substructure and foundation requirements. And again, our future speakers will talk about those elements. Thermal insulation, using a carbon fiber grid can provide a way to eliminate thermal bridging, provide for 100% composite action in panels, And as I said, they're easy to handle and fabricate. So those are the kinds of things that you normally see with concrete construction, with the steel begins to rust, stains, fall. You don't see that with carbon fiber grid, and they're very simple to use. You can use a handheld cutting tool to simply cut the carbon fiber in the process. Let me shift gears now and move into the precast, and then I'll follow it up with some applications for infrastructure. The Altus Group, and as my introduction, I'm the current executive director for the Altus Group. And so what is the Altus Group? Well, the Altus Group was formed by Schomerach and some of the leading pioneers in the precast industry in North America to develop innovation and bring new precast elements and technology to market. So our members make carbon cast precast elements using C-grid reinforcement for either enclosure systems or double T elements that make precast elements lighter, stronger, more energy efficient, and overall lower in cost than conventional precast products today. So our consortium was formed in 2004. The initial products were launched thereafter. And today our Altus Group operates with basically 19 member companies, more than 24 manufacturing locations in North America, and we have over 200 people selling the technology and generating more than $1 billion in annual revenue. So the key thing is co-opetition, pooling resources, developing the best minds, the best technology, and we were able to bring this technology to market in 6 years versus what it normally would take a new technology 10 years to achieve in North America, all through the formation of the Altus Group. So who are our members? These are the companies in North America and international. I won't go through the specific locations. Pat Hines represents Knife River Precast, our partner in Oregon. Schomerach is a founding member of the Altus Group and the exclusive supplier of the C-Grid patented product for the Altus Group. Simple overview of the various products that we make today. Basically, a high-performance insulated sandwich panel system. We have a ribbed architectural panel, the same product with an architectural facade, spandrel panels, and double T elements. We'll talk a little bit about each of those today. So, where do we use them in precast? Well, as flexural reinforcement for all the applications. And additionally, we can use the carbon fiber grid in floating marine structures, planking products, sound walls, and earth MSE walls. Something like Terra Armee in Europe would be well recognized in that category. As a shear connector, which Mr. Gwynn is holding in his hand, it's primarily used as a connector for sandwich walls as well as architectural cladding. And then we use the carbon fiber grid for confinement and piling applications. The use of grid is really limited to what the imagination and what the structural requirements for the application can be. So I'll just leave it at that, and we'll talk more about that as we go forward. So a typical double T structure, it looks something like this from a cross section. We're taking weight out of the top surface of the flange. We're replacing the steel mesh that's conventionally used in the top surface of the flange and replacing it with a bidirectional, a unidirectional carbon fiber grid. And some of you probably saw the element on the table. And we've done significant load tests. And the benefit for the non-corrosive is you can eliminate the cover requirement, and you can make your double Ts or your elements roughly between 8 to 12% lighter. But in order to use the carbon fiber grid, we had to think out of the box. So we developed an embedment machine, an automated machine that would actually take rolls of double T, automatically place it in the formed bed, cut, screed, and vibrate all in one step, eliminating labor. So it's an automated manufacturing process for double Ts that our members use in the United States. Very, very successful. Why? Corrosion resistance, durability. You also are eliminating the top layer of post-applied sealers that are commonly used in double T parking structures. Additionally, when you start reducing the weight of a double T, you can reduce the substructure, foundation, lower erection costs, lower operating and maintenance costs, and you're also saving time and energy through an automated process. This is a typical load deflection curve with a double T and a point service load. Again, you can see the pseudo-ductile type of behavior of carbon fiber grid to failure. These are examples of projects that have been done. In terms of parking structures, we have over 100 parking decks in North America using the technology. These are just a few. This was actually the very first structure we ever did. We actually made this one with 1 meter wide rolls. We fashioned them together, put them in the bed, and that's when we realized, we need a better way to do this, a machine. So it took us another 2 years to develop the automated machine to do that. But very successful structures. Many of these structures don't look like parking decks. They look more like aesthetic enclosed buildings, and many of the enclosures are, in fact, the externals can be carbon cast. Precast insulated walls. I won't steal much of the thunder. Pat and Larby will talk about this, but these are typical cross-section using the carbon fiber grid as a connector system between two sandwiches. We also use conventional steel reinforcement for economics. So the grid is only used as a connector in most of the applications. Again, we're using it for elimination of thermal bridging and high strength because we're producing composite pile systems or panel systems. Thoroughly tested in terms of fire performance, cross-sectional cutaway of showing the connector system into the panel. This panel was subjected to millions of cycles, so we know the structural performance of large horizontal and vertical panels. And Larby, I believe, will talk more specifically about these particular aspects. These are some of the projects that have been done in North America that are specific to wall panels, basically distribution centers, athletic stadiums, aquariums, high-rise multiplex. This is a dormitory for a major college and university, schools, distribution centers. So we cover the gamut. Same technology can be applied for architectural. Again, the difference being the tolerance capability of panels. You're still using the connector systems. And depending on the design, you can reduce the cladding weight to perhaps 50 to 67%. So excellent crack control. One of the benefits you get with carbon fiber grid versus other steel reinforcements is the ability to control and confine crack to specific regions, because you've got reinforcement closer to the surface and or as needed. Again, panels have thoroughly been tested for missile testing, for fire testing, and the second part of the test for fire in the United States is the must survive, the hose stream test. So guaranteed performance for the product. Architectural cladding, just some examples of high-rise projects that have been done. This product was Symphony House in Philadelphia, 20 stories, using a very lightweight B-ribbed cladding panel for the enclosure. Another project, the Heldridge Plaza in New Jersey. Many of our structures are thin brick or brick cladding. Other precast elements may typically just be architectural sandblast, depending on the structure, multicolor, multi-design, limited to the architect's imagination. All things are possible with carbon cast. This happens to be the first LEED Platinum project in the United States. This is a carbon cast architectural project. It was done almost 8 years ago, one of the first projects, a very, very significant award-winning project with a European type of style by the architects. The project that was done about 4 years ago, another dormitory. This happened to be in New Jersey. It's an insulated architectural cladding panel. Another technology that we're working on the precast element is piling. It's a technology that we believe has tremendous merit. Again, we're using the carbon fiber as confinement around steel strand. That's the technology today. It could be carbon fiber strand. It could be stainless steel strand. The transportation industry is looking at various options to produce piles that are square and or round configurations. That will be forthcoming, and you'll probably be reading about the press. I talked about sound walls, MSCs. You can use the grid as a reinforcement in sound and earth walls. All right, let's talk about some other applications outside of precast, just to give you a flavor. And I'm okay on time. I got about another 10 minutes to go, and I can do that. Let's talk about repair, shotcrete, and all right. This is a transportation project. This was a bridge in North Carolina. It was significantly deteriorated and corroded, deemed one of our many bridges that are in need of repair. Here they basically hydro demolitioned off the spalled concrete and installed carbon fiber grid as the structural reinforcement. Again, the grid was mechanically faced, and then a topical application of shotcrete or manual applied concrete was applied. The benefit was you could get an awful lot of carbon fiber grid on a roll in a very, very tight, confined space, eliminating a lot of labor. If you had to do that with steel, it took twice as long. Another application, topping slab. This is a specific project. It was a grain terminal. They had a long pier bridge over water that was stressed and deteriorated. They needed to put a new surface on it, and so we reinforced the decking with carbon fiber grid. They actually used the carbon fiber wraps on the underside of the beams to provide incremental structural support. And here we're showing how the carbon fiber grid was placed, and the topping was actually rolled out on top. So the grid was spliced at various intervals depending on the structural requirements of the project. Further pictures of the project. In the UK, we worked very closely with Morgan Est. Actually, it was Morgan Sindall, but it's Morgan Sindall now. But one of the crosses for the London Underground is actually a membrane liner reinforced with carbon fiber grid. Again, it was a manual placement, a manual trowel. But we proved that carbon fiber grid can be used with ECC, which is engineered cement composites, very high strength, high flex modulus concretes that they're starting to use in structural applications. And this is just a picture showing the weight, loading, and ductility of the segmental structure for precast. Number of tank lining repair applications. There are many corrosive environments and applications, so simply taking off the old concrete, reinforcing the deficient structure with C-grid. This happened to be a potash mine in Saskatchewan. Timber piling, rehab. You know, there are many deficient timber pile applications, simply jacketing and reinforcing them. C-grid provides additional strength and confinement reinforcement to grouting systems or concrete systems in a highly corrosive environment. Pervious concrete, again, an emerging technology. I think probably same in Europe. Again, if you want to reinforce the pervious for crack control, C-grid is the only reinforcement choice available. Parking garage or typical building structural surface repairs. In fact, this happened to be a parking deck that was completely destroyed by corrosion. The steel that originally had been placed was cracking, causing surface decking. They hydro demolitioned off the top layer back down to the original steel, came in and put the carbon fiber grid and recast the new surface deck. Slab on grade applications, no reason carbon fiber can't be used in decorative applications. Pool decking, obviously a significant corrosion concern because there's chlorine, which aggressively attacks the steel. And other composite reinforcements are simply too expensive. So why not use a C-grid to reinforce the decking and never have a corrosion problem. Decor, plenty of applications for light, thin structures where the imagination is limited. Fireplace lintels. When the housing market was going very strong in North America, concrete was the preferred decor element of choice, and I believe it will continue to have a place in the market. Balconies and slabs, use with hydronic water systems, so common use. This happened to be a project in Japan with PEX tubing, and they wanted a crack-resistant flooring material that could be subjected to temperature. Chemical processing plants, again, aqueous moisture environments destroy the reinforcing, so use carbon fiber grid to, in this case it was a repair, but why not put it in the surface original product. And finally, a historical reinforcement project in New York City, which is the non-burnt band shell. Here we were using ferro cement as the repair technology to redo a roofing structure for the product. So just to give you some idea, this product used a C12 25 by 25 millimeter grid structure to reinforce it. So just a couple of comments relative to using the C-grid in concrete construction. Self-consolidating concrete has really been the most innovative mix design in the last several years. Carbon fiber grid works very well with SCC. If you want to use a non-SCC mix, you can. It may require a little more vibration to consolidate the concrete and get it around the grid. You need to make sure that the aperture of the grid is sufficient to pass aggregate through it. So that's one consideration for sectional designs. In combination with other material systems, if you need to position the grid, you use it with conventional bolsters or other types of chairing systems with the depth of concrete required. And the splicing and development length is the only issue that you need. It varies. The splice length may vary from grid to grid depending on the development length for the product. And typically we have a 2 to 4 grid overlap minimum requirement. So just some concluding thoughts as I wrap up my presentation. Grids are durable. They certainly last longer. We've done work that up to 100 years. Lower maintenance and repair costs are possible. Lower life cycle costs with the use of a non-corrosive material. They don't corrode. You can reduce cover. Lower concrete is required. And you can use the carbon fiber grids, which can contribute to thermal efficient structures in wall panels and cladding, and you'll hear more about that today. Which then translates into a whole plethora of other benefits, from shipping to erection costs, less steel, and high development of highly sustainable building solutions. So, in summary, grids have been proven over the last 10 years to be a viable method for reinforcing and strengthening concrete structures. They have to compete with conventional materials on a installed cost and system basis, or they're not going to be used and specified, and we've demonstrated that. Like all materials, they are not a panacea for all applications. They have to make sense for the right application, and they have to be structurally designed for the intended use. And they are highly successful examples of CFRP reinforcement. So there's a bright future ahead. This is just the beginning. The market is recovering around the world, and we expect to take advantage of it. And we thank you for your interest in C-grid reinforcement and its possibilities today. So with that, I'll turn the program back over to Michelle and take any questions that might come.
You have seen John's presentation is about what grid is, with the application, and all that. But how do you design it? You know, the question always is when you have a new product that's put in concrete for construction, where do you start? That's the problem. And our codes, and it's similar to Eurocode, we have steel in concrete is governed by ACI, American Concrete Institute. And then within ACI, there is another committee that deals with carbon in concrete, and that's ACI Committee 440. But we don't have anything that deals with a grid, something like this. But in construction, you have to relate to a code. You can't just make up your own design formulas and then hope everybody will buy in it. So we had to relate to a code. So the closest thing to it will be a welded wire fabric. So we adopted ACI 318. The concrete steel and concrete, but we have used provisions of ACI 440, which deals with the carbon, but the problem is they're actually bars, carbon bar, but not carbon mesh. This is just a little background. So, but how do you go by it? Our code says that if you have a new product and you want to use the provisions of this code, you can use provisions for this code provided that you validate whatever you assume. So the Altus group used that approach, right? So we are using the same formulas as steel and concrete, and we just ratio out the yield strength, you know, from okay, it's okay. Maybe a little lower. Oh, okay. Is that good? Can you guys hear me now? Yeah. This will hide my face, you know. It's like this might not be a bad idea. So anyway, so I was saying that you use the code formulas and then use the same formulas you use, but you have to validate by test. And Altus Group has validated every aspect of design using tests. And the budget is roughly about $500,000 per year, and we've been doing this for about 10 or over 10 years. So we're talking about $5 million worth of testing. So we test everything: flexure, shear, fatigue, creep, shrinkage, fire, anything you can think of. As soon as we use a formula, we have to test it to validate it. So in my presentation, I'm going to go through the things that are different than steel and concrete, right? I'm just going to go through a flexure, through all aspects. Which formulas do we use? And then go into some products, you know, and then finally give you how we design for fire also. I understand it's a fire issue here, so I got also a prescriptive design to use fiber, okay? Okay, so you had this presentation. What is a carbon fiber? It's basically, John went through it. It's in a roll, and it comes in unrolled like this and used in lieu of usually welded wire fabric or some very close knit rebar. It can be used as primary reinforcing. So we specify it. When you buy a grid, you specify the size of the grid, right? The thread size and the spacing. And John gave you that table. So basically you want a C50, a C100, and you want it at 5 centimeter squares or 10 centimeter squares. That's how you buy a grid, and that's how you use it in design also, okay? Some applications, they can be, as I said, overhead. They can be put in a precast plant, or they're automated also, like the machine that John showed. You know, you can do it either way, so an easy placement to do. You've seen this graph. Basically, the ultimate rupture, the yield stress of the grid is about 2 gigapascal, and the modulus effect is about 205. He is right. It is a brittle material. You have to keep that in mind. However, when you put it in concrete, it exhibits a pseudo-ductile behavior. Why pseudo? Because in itself, it is a brittle material. But when you combine it with concrete, you got a very good ductile behavior. And you've seen the graph that John showed. You actually get a good ductility, but we never go into the plastic stage. Although you get that ductility, it's a good added bonus, icing on the cake, but we never use it. We typically design right below the rupture, always below the rupture, okay? We keep that in mind. We use also reduction factors before you even use any of those calculated terms, like these. Any of the calculated terms, you apply an environmental factor, and these are in your presentation. You can see. So basically, just to take into account that there are deteriorations that you need to account for that, and then the modulus of elasticity, the shear modulus of elasticity, is also calculated using the general formulas. So we do have a G. Why G is so important? It is important for sandwich wall panels because to gauge your composite action, you need this term. You need the actual G in order to calculate the deflection properly. The general formulas is the same as concrete, right? So in lieu of steel, what you have carbon fiber. So the behavior has been tested, and it reflects exactly the general behavior in concrete, right? So if your strain is higher than the 0.85 of the concrete strength, you have a crushing failure, you have a balanced condition, FRP. So this is exactly the same as steel, okay? Except now the F, the modulus, the yield here is much, much higher. You're no longer dealing with 60 KSI, you're dealing with 250 KSI, a much higher modulus. But the general formula is the same. The concrete block also has been tested, and we found to be exactly the same as concrete. Replacing the carbon with steel works exactly the formulas they are in concrete, and it's the same. So your Eurocode formulas will work exactly the same, except using the strength of the steel, you use the strength of the fiber. One thing to be the difference between steel and carbon fiber is it is never used in compression. Why? Because it has no buckling capacity, and it has no really a good vertical strength. So it should never be used in compression. Don't use it in a column. And then if you happen to have a grid in your compression block, you need to ignore that. Typically in steel, you can account for that and use it for your design. But if you have grid even in a compression block, just go ahead and ignore it. For creep and shrinkage, we have done a creep test, and the formula is there. If you want a long-term creep, it's 0.6 times the creep coefficient. This is the standard concrete creep coefficient. It's the same in the Eurocode, times your sustained deformation. So if your sustained load is 5 centimeters, your creep coefficient times 0.6, you get your long-term creep and shrinkage. That has been tested, and this formula verified. Then if you have a sustained load, if you have a load that's permanent, I'll give you an example. When you have a sandwich wall panel where your interior is structural, you have the isolation in the exterior, but the exterior is not grouted at the base. It's really hanging from your structural wyeth. That load is sustained on the grid. And then for that grid, we usually do 0.55, right? The way we tested it, we started loading a grid at 0.4, 0.5, 0.6, 0.7, and then kept it for a whole year and we saw that it broke at 0.6, but it didn't break at 0.5. So we tested 0.55, and it didn't break, so that's where that 0.55 came from. It's not analytical, it's all by test. For fatigue, we have done also our own fatigue tests, and the general formula is based on the number of cycles. So you reduce your strength by this formula, and that works also for Eurocode or any application as well. So your fatigue stress is something like this. I guess for about 1 million or 2 million cycles, you get like to 0.45 or something like that. But we have a formula for fatigue as well. For shear, it can be used for shear the same way you use welded wire fabric. So in a vertical long beam, if you typically use a welded wire fabric for your shear strength, well, you can replace that shear strength with the grid also. But as a stirrup, very, very hardly used, except for piling, where you actually shape it round, but you cannot make squares for a beam or something like that. You can, but it'd be very, very not cost effective. For composite action, you have seen, that it can be used when it's cut at 45 degrees. You can use it as a shear connector. And I'm just going to give you the general design formula that's different than any other connector. All the values, the capacity of the grid, of the system, the capacity of the shear flow is all determined by test. So there's no analytical formula to determine what is the capacity of your grid. We have now tables and formulas depending on the thickness of your insulation, the type of insulation, and the spacing of the grid. You can calculate the shear flow capacity of the grid for that application. This is the test we did. And the failures we get, typical of a truss, you got a buckling, and you have also tension rupture. So it is validated by test that the behavior is a truss. There is an example of a panel that has grid reinforcing, but shear grid as a composite, something like this. We have done extensive tests on this to validate that. There's a type of application. You can see it. This is an EPS, a white bead board, with the grid already placed in both directions and the concrete on top. So the application is very, very simple, and you get a very nice sandwich wall panels. So to come up with the formula, what is the capacity now of the grid in that insulation? It's very simple. We have now a formula to do it because we tested everything. We tested EPS, and we tested different thicknesses, and we have tested different spacing of the grid, because all these 4 elements, the three basic elements, affect the capacity of that system. So we did it for EPS, XPS, sandblasted. So basically, we roughened XPS. We took off that film, that shiny film, to get a good bond out of it. Or XPS unroughened, it's regular XPS, and then the polyiso. which is the most expensive insulation we have in the US. And then we get the formula. So the general formula now becomes, instead of doing an analytical analysis, what's the capacity of the grid? It's very simple. Your capacity, shear flow capacity of the grid in that application is because the base. The base is the one for 50 millimeter thickness of the insulation, 2 inches, and then the grid spacing is 24 inches. So that's the base. You take that, which is about 270 kips per inch, which you can translate to newtons per meter, and then you multiply by a factor of the type. So depending on the type of insulation, there is a factor you get from a table, times the factor of thickness, depending on the thickness of the insulation, and then times the spacing of your grid, and you get a shear flow capacity. So it's really a no-brainer. There's no need to get into really, integrals or derivatives or differential equations. It's very, very simple to come up with the capacity, and it's all by test, okay? And we've done a full-scale test to validate all those approaches. This is like a full-scale spandrel, you can see, with the chamber. We've done a vertical application, load-bearing vertical application. We've done horizontal applications with a push. And we've also done like cyclic loading too. Show you this video. Let me see. Oops. Yeah, very, very long, huge deformations just to prove the composite action. I think this panel is a 242, which is a 50 millimeter, 100 millimeter, 50 millimeter. And it went up. I'll do it again. As you can see here, very large deformation. And it was designed for about a 90 mile per hour wind service, and we kept going. It went up to 250 mile per hour wind, which is extreme hurricane category 5 Florida type of wind, and it withstood that, okay? Now, the definition of composite, there's always everybody debates, what's a composite, what's a non-composite. Very simple. A composite panel, something has to have, its strain being almost parallel, mimicking a solid panel, right, with a little deviation because you don't have the same mass. Huh? A non-composite is the two wires really operate independently. So when we do our panel with the C grid, we get really a very, very close composite. This is a composite panel, a true definition analytical composite panel, and this is a tested analytical panel, Altus panel, and you can see that you really achieve a composite action between the two wires. You don't have to. You can use a grid for a non-composite application if you want. But we typically like to have our panels be composite. And we have done, you can see the two, between a non-composite, a composite, and a solid. And you can see that all the deformation correlates really within each other. So the composite behavior has been proven by tests several times also. Now for the shear flow, to design the shear flow, for the French would be cisaillement horizontal, and I don't know what others call it, but that's how you design your grid, right? You come up with what is the shear flow demand between the two wires. That's how you design your connector. Not necessarily a grid, but any connector. That's how you design it, right? You need to have your capacity times the reduction factor has to always be higher than the demand. Okay? And the demand is your shear times your first moment divided by the moment of inertia, VQ over I. And we do have two different factors. I wanted to bring these two reduction factors because we differentiate between service and handling, because when you handle it in the plant, it's really temporary. So you don't need a very, very high reduction factor. But in service, you do a higher reduction factor. And typically, the stresses are much, much higher in handling than they are in service. So we try to get another 10% benefit out of that. So you do your handling. So this panel, for example, there's your moment, but there's your shear, and your shear flow is really the same, like this times Q over I, right? You do it for your handling. You do it for your service, right? You got your shear, your service, right? And then what you do is basically you place your grid in such a way. Obviously, there's more steps to that. We have design examples which you guys can follow. But the end game needs to be something like this. At the handling, you have your grid capacity, right, has to be higher than your demand, right? This is obviously a very conservative design, but you can bring this all the way down to here and even violate some of this peak as long as the area under the curves, which gives you the total shear flow capacity, is always greater than the area under your demand. So you do it both for handling because they have two different factors, reduction factors, and you do it for your service. So this panel will satisfy that composite action. And as I said, this is a very conservative design. You can bring all these down if you want to. Some typical connections, in a sandwich panel, we have to maintain continuity between the insulation in both directions, so we are very conscious of that. So anytime we need a much deeper to place a plate or to place an insert or something like that, we create a trough, just thicken, reduce the insulation behind it, create a trough so you can place your elements. But you take a hit as far as thermal, but at least you have it out to out, top to bottom, and the hit is usually very, very low, 10, 15% reduction in your R value. So, but you have to do it, very thin when you have a 5 centimeter wyeth on both sides, and you have to put inserts to lift it. You have to reduce your insulation so you can get the insert in there. Or you need to put a gravity connection, you have to reduce. But we never, in our practice, we never bridge the two wyeths with solid concrete. The only thing that crosses the two is always the grid. Never steel, never anything else. And we have done thermal testing also to see the reduction, and the reduction is very, very small. And we have formulas to calculate that reduction also. Now, this is an application into a CIP. It's the same thing. As you can see, they're your typical connections we use in the US. So when we need really to make sure the two wyeths work together in an application like this, we put grid on both sides of the connection. This is what we call a knife plate bearing connection. I don't know if it's common in Europe, but we do it in the US. We just use a heavy plate that sits on a bearing, and then we have a trough right behind it to thicken the concrete right behind it, but we never, ever bridge it. Huh? This is also another picture of the knife plate, also another bearing connection. And then these are tiebacks when you don't have access to a corner. That's how we do it, so that we give some flexibility. I'm going to talk about double T's quickly. How am I doing, Michelle? I got 5 minutes? 10 minutes? Okay. For double T's, I'll do the design of the double T's also, but this is a typical parking garage. This is very, very common. We have millions. Double T is one of the biggest products in the US. We sell millions and millions of them, square meters per year. So for the grid distribution and the general formula, so basically your moment is just the same as your concrete if you were steel. Instead of Fy of the steel, we use the capacity of the grid times the number of grid. If you do in design per meter, how many per meter, times the capacity of the grid itself in tension, and that's how we come up with a moment capacity. For shear, we never use the grid. Although it has some shear capacity to help you in shear friction, we always ignore it. We always use the shear capacity of the concrete, and this is our formula in our code. Something similar in Euro, but you just don't have the square root in there. For cracking, as you said, our codes got away from checking the crack width and all that. I know the Euro code does that still, but in our codes we don't do that anymore. So what we do, we limit the tension to the cracking. Our cracking limit is 7.5 square root. Euro code has a different one. But if we limit this, then we are crack free. We don't have to worry about crack width. We've done the load test. Was done in a chamber for a uniform. This is what the chamber looks like. So basically, you put your T's and then you suck the air out, and that gives you the pressure. That's how you apply the load. And then we measure the deflections to verify the formulas we are using for designing that grid, and it correlates beautifully. And these are tests for a point load. So we do a point load here, point load there, point load at the corner, and then verify the angle. Like we assume an angle of about 60 degrees. Then we calculate that angle. It's actually much higher, but we kept in our design as 60 degrees. And we tested that flange in all applications to verify our design formulas. For fire, we have both tests, but if you don't want to do a rational design, we have formulas also for rational. So basically in our code, you come up with your moment under temperature, so you don't use any over-strength factors. You don't use any load factors for fire. It's the same in the Eurocode as well. And then you do the same thing for your shear. And what we do is we do a prescriptive design. We will have temperatures, if you're doing for 2 hours, you come up with your temperatures at a variation for concrete, and then the temperature at the grid. Based on the temperature and the type of concrete and the cover, you can get a strength reduction for concrete, depending also on, so you get your strength reductions. And then for the grid, we have our own curve, depending on the temperature. This is in degrees Fahrenheit. It gives you the reduction. An average, a regular one, which is about 1,000 per yard. Depending on the temperature, 100 degrees, you're dropping, and then as you go to 100, you keep dropping, keep dropping, keep dropping. So depending on what's the temperature for 2 hours, you come here and you get your strength reduction for your carbon. And the general formula, you calculate what's your concrete strength under fire. This is also a prescriptive method that's in our codes. And it's probably similar to the Eurocode also. Come up with your stress block, and then you calculate your moment. So your capacity of your moment is in the capacity of the grid reduced by fire times the number of grid you have times your D, which is the moment arm. And then you make sure that your capacity under fire should be greater than your demand under fire. That is a typical prescriptive method, and we have publications you can use. Or you can use our tests also. The same thing for shear. You do the same thing for shear. So we have a prescriptive method that has been validated by test, and this is the type of test we use, right? We have a test, double T in a chamber. We load it up under fire until failure. And then you validate. You put all strength gauges, you measure your temperatures, you measure your strength reductions, and everything correlates. So we have that prescriptive method, and it's in our publications as well. That gives you an idea about the things that are different. Okay, there is more to it than this, but everything else is exactly the same as steel and concrete. These are the things that makes it a little different. And we have publications, we have design examples you can follow. I think Michelle is going to spend also a lot of money to make a metric, right? Eurocode and metric, yeah? I'm vying for that contract. But it will be done. It will be done. It's a matter of conversion. It's very, very simple. And in the US, we try not to complicate things, make them easy to design, and I hope you guys will adopt the same method. There's no need to complicate it because it is not a very complicated product. It does not require to be complicated. Thank you very much.
Thank you, Larbert. We're going to take a short break.